Okay, so we are going to quickly go through raw pointers, and after going through raw pointers, understanding what they do, not understanding, kind of review everything from IPC 144 till now. Then after that, we are going to talk about smart pointers, and that's it. The next class that you're going to have, you are going to have a quiz. And the quiz is going to be about binary files and seeking back and forth in a file. So that's going to be your quiz, because I want it to be a very short quiz before I talk about parallel processing. And then the next quiz after that, we're going to go to algorithms and stuff. But for now, we're just going to do the file for this week. So essentially, I'll give you a complex a class, and I'm going to tell you that there's a file that has binary records of this class in it, and your job is going to be read and modify a record in the middle of the file, display the last element, that's last record in a file, the first record in a file, and then I'm going to ask you to display everything in reverse in the file. So this is going to be your quiz. You're going to see it the next time you're coming in. Now we are going to talk about, quickly go through basic pointer setup. So again, a review. We talked about pointers. We said pointers are essentially variables that hold the address of other variables. And they are represented with an asterisk coming after a type. And that asterisk with the type together mean pointer. So integer pointer PTR over there is holding the value, the address of the value. You can indirectly access the values using a pointer, and that's the purpose of a pointer. So you can actually get out of the scope of a pointer and use it to access the values remotely. So, then we talk about pointer arithmetic and how do we traverse through the array. So this is the basic pointer that we have. So I'm going to put over here a basic pointer. Okay, just organizing my windows. Okay, this is good. So next, talking about arrays. When you actually create an array in C language, what we have in C language, the array looks like something like this. So let me bring it up. So the array that you have in the array that you actually see is something like this. So if I create an array of 3 up 3 by 4, you're going to have 3 rows like this, and you're going to have say 4 columns like this. And just give me a second, let me bring up the notes, just one moment. Bring this down. All right. There we go. Yeah, so as I was saying, then I could have something like this. And when you create an array like that, you usually see something like this. So if you have an array of 5 integers, that's what you do. A pointer arithmetic over here works like this. I'm going to first show you the pointer arithmetics, then we're going to go to the RAG structures and dynamic pointers and understand exactly what they are. So let me pause this one. I'm going to bring it back later. So when we are talking about pointer arithmetic, essentially we are talking about adding values to a pointer back and forth and see how actually it affects the pointer. Having that, okay, so when you have an array name, we know that the array name is actually pointing to the address of the beginning of the array. In here I have an integer pointer starts that holds the address of numbers. Essentially it points to the very beginning of the number. And then in a loop over here, I'm going through every single element of the array using the pointer. So the start plus I that you see is actually receiving one integer, adding one integer to the start pointer. And if that one is 1, then the size of the target of the start will be added to it. Therefore, start becomes start plus 4. And then when I becomes 2, then it becomes start plus 8. And that's how the address within the parentheses over here points to the next point, the next element as we are going through. That line that you see at line 11 with star start plus I actually is called the pointer notation for an array. It essentially means that you can actually use an array like that. We could have written this like this. These two would have been identical. So if I have something like this, I could have written over here numbers, because I'm not changing the numbers by itself. I'm not changing the array. Therefore, the address remains the same. I could have used line number 12 instead of 11, but I'm using pointer just to emphasize the fact that pointers and arrays are exactly the same. So essentially running this code, I'm going to run the code and go through it one by one. Running this code. We can see that the arrays are created and the sum will get, it actually finds the sum of all the array. Now take a look at here. When I write numbers I, so it says numbers I, so it prints numbers I, then the value of the target of start plus I and start plus I by itself. So essentially it says number 0 has the value 10 and it's at the following address. The address that you see over here is actually a hexadecimal one, because I'm just printing the pointer by itself. And obviously I'm going to have the sum. After it shows all the values, I'm going to actually see the sum. So this is part of pointer arithmetic that I was talking about. Now, if I want to see the address the way I can actually understand it, I'm going to make this long, so it becomes as long as the size of a pointer. So now, if I run the exact same thing, you will see that the numbers over here are being added by 4 as I'm going forward. So every address is actually 4 bytes bigger than the other one, and that shows that the array is linear in memory. Now I'm going to have another pointer holding the numbers, but in here what I will do, I'm doing the sum the exact same way, so we can actually show the values to see what I'm talking about. So in here I'm going to say C out numbers I is, in here I can say either PTR 0 at all times, or target of PTR. So these two are identical, no difference between the two. I'm going to print them both so you can see what I'm talking about. I'm going to say or target of PTR. So what happens over here is this. Because PTR is now starting from numbers, obviously the very first one is the one that you're seeing. Let it recompile. Don't tell me it hung. I think it hung. Let me do it one more time. Cancel. So I'm going to stop the thing and I'm going to run right to this point again one more time. So yeah, I was here. Now what I will do over here, I would say target of PTR sum plus. So this essentially is the first element. And if I print it, you'll see. So both actually PTR 0 or target of PTR will show 10. Then I add 1 to PTR. When I add 1 to PTR, now PTR is pointing to the second element. Therefore, now PTR 0 is 20 and target of PTR. This is literally the best thing that you can demonstrate for pointer arithmetic. When you are adding 1 to the value of the pointer, it automatically jumps to the next type that pointer is pointing to. Since it's an integer, it's always +4. So therefore, PTR 0 or target of PTR are identical values for that. And then the sum is whatever the sum is at the end. So this is a demonstration of pointer arithmetics. Okay. But this is where the pointers are used to traverse through statically allocated memory, which is very fine. No problem with that. But pointers are also used for dynamic memory access. So essentially, I'm not going to run this just because this is like a OOP345 week 2. So what we are doing over here is simply having a dynamic memory, dynamic array of certain size. One by one, we can get the values. And after line 15, that dynamic array has no difference with the numbers that we had before. Therefore, it works the exact same way. So if you say dynamic array +1 PTR, then it becomes the second value. It skips the first one. There's absolutely, it works exactly the same way. So pointers work the exact same way. The only difference is line 29 is that now I have to delete the pointer. When you delete the pointer, you're actually deleting the target. And doing dynamic array is equal to null PTR is what we do not to have a dangling pointer, but when you think about it, it wasn't really necessary because the program is about to end. Who cares if it's null or not, okay? But if you are ever in doubt if the pointer is about to be reused for another dynamic memory allocation, you always keep it null to flag it for it to be null. So this is again, these are just quick reviews on what we have talked about before. Another thing about pointers was using pointers to actually access compound types. For compound types, I don't think this is, oh, actually this is the one. Is this? No, wrong one. Okay. For some reason, as soon as I close it, it goes to the last one, which I do not want it to go. There we go. So now I have a structure. Structure has a title and a grade. And in main, when I create an array of courses like that, I can use the pointer with a compound array exactly like a regular pointer, absolutely no difference. So a regular array, absolutely no difference. It works the exact same way. The only thing about this here is when you're actually using a pointer to individually point to a specific thing inside the structure. And that's where the arrow operator comes to play. So when you have a pointer pointing at a specific structure, then you have to use the arrow to access the values inside the structure. If you don't want to use that, then you have to use the ugly version of target of PTR and title. This is too many things to type and very difficult. Like this is much easier. So when you have a pointer that is pointing to a structure, use the arrow to access it. Oh, this is like a mixture of everything. It's with compound type and pointers, dynamic pointers and everything. Again, this dangling pointer being set to null is unnecessary here because we are not using it, but it's good to have it as a habit. Now this is the part that this is the part that I was talking about. A, B, C, D, where's my, okay. Just a second again. Okay, so I drew this last time to talk about, whoops. Let me bring this down so I can maximize the other one. So I was talking about a two-dimensional array like this, and I said when you create a two-dimensional array, this is what you have. So essentially, when I do something like this, when I create a two-dimensional array, something like this happens. Essentially, what we have in memory is a table that we create because it's 3 arrays of 4 integers. Therefore, the index over here for every and each, this is 0. And this becomes 1, and this becomes 2. I know, boring, but we have to go through this to understand exactly how two-dimensional arrays work. And this is 2, and this is 3. Okay? And the values that we have, again, we know that the values are, this is 1, 2, 3, 4, 10, 20, 30, and 40. The point I want to make over here is that obviously when you do something like this, 30, for example, over here becomes A12, which means A row 1 and column 2, and you get 30 out of it. But let's do something different. What if I actually create a single pointer to this two-dimensional array? If I do something like this, what happens is that I'm going to have actually 2 pointers pointing at this. One pointer is the A, pointing to the beginning, and this is the A. And the other one is going to be, PTR, pointing to the exact same place. The difference is that A is a two-dimensional array. PTR is a single-dimensional array. So what happens? What's the difference between the two, essentially? Take a look at the codes that I'm about to write and see the differences between them. First of all, let's have the end of the thing first. So we're going to go end. And let's start with these two. So if I say print PTR 0, essentially I am treating that pointer as a single dimension array. When I say print PTR 0, obviously 1 is printed. And when I say print A0, A00, it's the same. So therefore, the outcome of this will be both 1. Now, let's bring this one left. If I say target of PTR and target of A0, the outcome is still the same. Now, this gives us a message that A0 has the same type of PTR. Therefore, A0, A1, and A2 are actually single dimension pointers. It's simulated that way. So if A0 is a single dimension pointer, we know that the size of the target for A0 is an integer, it's 4. That's why when I say A01, it goes to next integer. But what happens? Yeah, so as a result, I could do these. And you know that it's going to print 3 and the other one's going to print 3 too. I'm not going to go into detail on that. But if I over here mention don't know what I'm going to put in here. In here, I'm going to say target of A1. I can do that because A0 was the target of the first array, first element, that's 1. So obviously, target of A1 is going to print 10. So if I comment this and I print this, we know that that happens, right? It's printing 10. Now take a look. I'm going to remove this one. And for this question mark, I'm going to put something that doesn't make sense, which is 4. Because we say if PTR is a single dimension array, after 4 it should be someone else's memory. But when I actually, after the index of 3. So 4 should be at right side of 4 in someone else's memory because I have 3 arrays, 3 single dimension arrays. That's what the definition of double two-dimensional arrays are. But when I run this, I'll notice that that is 10 too. Which means PTR4 that continues, actually goes to the second line, which means the two-dimensional array doesn't actually exist in C language. A two-dimensional array is essentially a single dimension array that is divided into 3 pieces. These are supposed to be equal. Let's assume that these 3 sizes are the same. Now, when A is pointing to the beginning of this, they simulate it in a way so A0 becomes a pointer that points to pack of 4 integers. That's why when you say A0, it means the first chunk. When you say A1, because A1 size is 4 integer, it's going to jump 4 integers further, therefore it comes to the second chunk. And from there you can go to the elements of the individual arrays. But we need to understand that a 2-dimensional array is actually a single-dimension array simulated to be 2. And that's it. Okay? So because of that fact, I can write weird stuff like this. Sorry, I need to, there we go. I can write weird stuff like this, and the program still works. Let me comment a few of those so I can actually see what is being printed. I'm just going to comment those so these come up, so it's visible. But when you look at it, when I say PTR5, it becomes 1, 2, 3, 4, 10, 20 becomes PTR5, but I can't say A0 and 5. If the array wasn't continuous, that 5 over there would have gone outside of the limit of the array, and I would have got a mistake, but that's not the case. 5 over here actually goes to the second one. So again, remember that this is a simulated one, and therefore the size of the pointer A over here is actually 4 integers, not 1, and that's how they fix the problem. So it's just a simulated thing, and be aware of it. And as a pointer representation for both of these, I can actually use this methodology to say out target of PTR plus 2. That essentially means add 2 to an integer pointer, go 8 bytes further. But because when I say over here A0, then that becomes a regular pointer and works the same. But if you write something like this, obviously the results are not going to be an integer, but the result is going to be actually a pointer. So you're essentially telling to add to the address by 2. And that's the nature of multidimensional arrays in C language. All right. Two-dimension pointed by one-dimension pointer. The next thing after that is creating ragged arrays, which essentially creating kind of a dynamic two-dimensional array. Take a look at this. Now I'm creating an array of 3 pointers. So what happens is that in that array, AR, ARR, the array, points to 3 arrays of type integer. type pointer to integer. So this is what we have over here as statically allocated. Then after that, I'm going to say AI0 is 1, 2, and 3. Therefore, the first one is going to point to 3 integers. The second one is going to point to 20 integers. And the third one is going to point to 30 integers. What happens in memory is like this, but when you're actually writing a code, it looks like you have a two-dimensional array. Take a look. Let me comment this. So in here, I can say something like for integer I set to 10 and I less than 30 and 10 and I less than 40 and or 50 and I plus plus. I can say ARR1 and then over here let's put 0 to 5 is set to something like 0 plus 10, something like that. So if I write something like this, it looks like a two-dimensional array, but the fact is that it's been built using an array of pointers and some dynamic stuff. Because the length of each array is not the same, now I did it like this to show you that the arrays of everywhere could be anywhere in the heap, but when you think about it, you should think about it as something like this. (10, 20, and 30), which means each column has a different size. These type of things are very dangerous to work with because problem is that you think it's like a two-dimensional array. You don't know the first one, if you pass 10, it's not going to go to the next column anymore because it's in a different place in memory. That actually going to crash the application. So you've got to be careful about that. So these type of array are called RAG two-dimensional arrays. And to delete them, you have to go one by one through every single one of them and delete them. Now, if you want to, you can always make them the first one that you have over here too as a dynamic one too. So essentially, instead of creating an array like this, I can create an array like this. I can create an array that is pointing to, say, of array of 4 pointers. Obviously, because each one of these is an integer pointer, what is pointing to them should be an integer pointer, which is here. When I have an integer, when I have an array of integer, I have to make it an integer pointer. So if I want to have an array of integer pointer, the pointer should be an integer pointer. Therefore, it's a very simple logical conclusion out of it. Because each one of them is an integer pointer, this one should be an integer pointer. So if I want to actually show what it looks like, this is going to be an integer pointer, and integer pointer, and integer pointer, and integer pointer. So the types are that. And therefore, in here, it's going to be integer pointer and pointer P. I'm just putting a different color to see that this is just a pointer to a type. That type happens to be a pointer. Now I can create an array out of it. So by doing that, it's exact same type of array that I created, but the difference is that when I actually want to delete the values for this one, I need to afterwards delete the original two. Delete the array of pointers too. So I have 4 pointers over here, dynamically allocated, pointed by P. Then each pointer separately is pointing to a different array. Therefore, at line 25, when I want to deallocate P, first I have to deallocate all the pointers and then deallocate the array of pointers by themselves. And that's pointer to pointers. Another way to demonstrate why pointer to pointers are needed is this. Say I have this. So when I run this program, obviously, let me clear these. When I run this program, clearly I'm going to have the values 10 and 20 printed over. There is no question about that. But what if I want to write a function over here to do what's happening at line 10 in a function? So I want to write void, something like advance. Then in here, I want to pass the PTR to the advance, not with C++, in C format, using pointers. If I want to do that, what do I write over here so I can, what do I write over here? So I can write over here target of P++, and the PTR pointer is added by 1. If I write over here integer pointer P, and I write over here advance PTR, and I show the PTR again, well, we'll see that the pointer is not advanced, but the value the pointer is pointing to will be advanced. Take a look. So 20 becomes 21. Because PTR is pointing to 20 at the moment, when I pass the PTR over here, it says add to the target of P, which is essentially PTR. Therefore, 20 will be added by 1. But if I want to pass PTR itself to here and make this advance, make the pointer increase by 1, I have to pass the address of the pointer and receive the address of the pointer. Now, doing this, the outcome will be $30. So just to kind of put an emphasis on it, I'm going to overload this. I'm going to put one over here as P and the other one as S. So you'll see exactly what the difference will be. Line number 17 passes PTR by value. Therefore, P at line 4 will receive the address. And when I say address of P is being added, it will go to where P is pointing, where is 20, it adds it by 1. In the second one, I am not passing PTR by value, I am passing PTR by address. Therefore, the address of integer pointer goes over there. Therefore, I need to receive an integer pointer. When I say add the target plus 1, it's the target of P in line 7 that will be increased by 1, which is PTR at line 19. Therefore, it advances to the next one. And that's what pointer to pointers are used. In C++, we kind of fix that. Let me make this, sorry, I'm going to make this one 4 because I want to advance one more. And then in C++, we fix that confusion by doing something like this. But that's going to cause trouble. I'm going to put it in the other one. So this is sure. Okay. So in here I'm going to say gptr pointer to pointer.cpp. So what we do in C++ is saying that we're going to pass pointer reference. That reference makes it completely different. Now, if by adding just 1 ampersand over there, this is what happens. What's going on here? So pointer reference P. Oh, pointer reference. So P becomes a new name for PTR. Oh, I don't need that anymore. I'll do this. Sorry. So C++ says you can write function at line 4. C language says I'll accomplish the same thing with number 7. So one PTR is passed by reference. Therefore, you are changing the value of PTR when you are adding 1 to P. The other one says I'm passing the address of the PTR, and therefore you will change the value of PTR by changing the target of P. And that's the reference of a pointer. That's that. So that's all about raw pointers. And we don't have anything else to talk about. Now that we know exactly what pointers do, we are going to create pointers of our own. It's 2:17. We have till 3:15. Let's go for a break. Come back because my head is hurting, and yours I know hurts more than mine when this is finished. So after, we'll go for like 5 minutes, and I'll come back and I'm going to show you what we can do to kind of make the pointers safe in C++. 5 minutes break. I'm going to pause this. Start recording. Okay, so now we want to kind of get rid of the problems that we have with pointers and dynamic memory allocation. Whenever we have dynamic memory allocation and pointers, we have problem because the pointers, we forget to delete them and we have memory leak. Or by mistake, when we don't have to, we point to the same memory location twice. So when one of them gets deleted, the other one becomes a dangling pointer and things like that. So we have two scenarios essentially that we have pointers in dynamic memory allocation that causes trouble. First, when we want to uniquely point to a specific type of memory, piece of memory, and try to delete it, and make sure that two pointers are not going to point to the same place, and we try to delete it when the time comes. Or the second scenario is that we want to be able to point to the same piece of memory with 5 different pointers, But we want to make sure that we only delete that when the last of these pointers are being removed or gone. So then what do? The answer is we're going to create a template. So we create a template, new item. I'm going to create a header file. And let's call this header file a unptr for unique pointer.h. So the unique pointer of mine is supposed to simulate a pointer that's job is to make sure only one pointer can point to a piece of location, and when the pointer is gone, the memory is deleted automatically. So to do that, what do? Well, of course, I'm going to create a template, and the template that I create, obviously, is going to have, so that's template type, and I have the class over there. Okay. Obviously, I need to manage a pointer, so there is no problem with that. And I need to be able to delete this pointer when the time comes. So for that, I create a private method called cleanup that cleans the pointer when the time comes. Okay, so those are the two things that I started. So obviously, to fix the problem with when the program ends, it will delete things automatically. The quick fix for it would be I just create a destructor for it and call the cleanup. So when I have a pointer, let me actually add something over here to it, a constructor to build this pointer. So I'm going to create a constructor, so unptr. And in this one, I'm going to say I'm going to pass a type pointer, ptr. By default, I make it null ptr. And I'm going to say set the mptr to the pointer that I'm giving it to it. And to make sure that no funny stuff is going to happen when it's setting, I want, when the pointer is being set, I want to be a dynamic piece of memory that no casting and stuff is happening to it. Nothing behind the scene. I want it to be a genuine pointer. So I want this constructor to be called like a constructor, not to be set to, not be assignment at the moment of creation or anything like that. I want it to be, make sure that constructor is called as a constructor is supposed to be called. Therefore, I'm going to put explicit over here. Explicit essentially tells you, hey, when you are actually creating this thing, it must be set the way the constructor is called normally. So what I can do in here is this. Say, to test this thing, obviously, I want to have something that actually makes it interesting. So I have an employee class that you can get its salary. You have a constructor to create it, and then you can print it out and all the good stuff. So a very normal type of class I created over here. So I'm going to minimize it. It's very simple. We're going to come through it later. So now in here, I'll be able to say something like unique pointer employee, P, new employee with this information, and I do not need to delete it. Okay? Take a look at this. So so the new that I create, when I actually run this program as is now, when the unique pointer is created, the new employee is created, obviously. Then it goes to the constructor of UPTR and sets it to value that it's supposed to. Now at the end, it goes to the destructor of the template and therefore it's deleted. So no deleting is needed for anybody who's using my unique pointer. Got it? That's number one. So we fixed the problem with deleting. It will delete automatically. I don't need to worry about it. Number two, I have to make sure that this pointer is a unique pointer and nobody can point to the same location of memory again. How someone else can point to it? If somebody creates an employee pointer Q, and then equals it to P. Now, two pointers are pointing to this location. I have to prevent that. How do I prevent it? We have the tool for it. The tool is to prevent copying an assignment. So copying an assignment is not allowed. Therefore, nobody can create a copy out of an already existing thing. So problem is solved. But what if somebody wants to move a pointer around? What if I want to do this? That should be allowed. Why? Because, did I put Q in both? Why that should be allowed? Because if I am moving a memory from P to Q, still it's only one. It's unique. So that should be allowed. And that is very simple move constructor to write. So what I need to do is simply go over here and say, hey, if somebody wants to move another unique pointer to me, I got no problem. I'm just going to set my pointer to the other one and make the other one's pointers null. Therefore, I will own their thing. So now it's done. There's no problem with that. I can do the exact same thing with move assignment. Which means if somebody creates a point, another one, another employee, they should be able to say, hey, I want, for example, now Q to be set to move R. So I want to move something from R to Q if I want to do that, or I want to assign. Oh, like things like that should be able to happen. So I need to be able to move one thing to another, and if that's the case, it's very simple. I simply need to make sure they're not the same, clean up, move the other one over there, and I delete my own, I take over the other one, and they're both null, and life is beautiful. So like this, the pointer will remain intact and unique. Now the only problem over here is, how can I actually do this? How can I say print target of Q? Actually, that's pretty simple too. We learned that from OOP345. All I need to do is to give access through an operator overload. So all I need to do over here is to do something like this. So I'm overloading the unary target of operator, and I simply say, or dereferencing, whatever you call it, and I'm going to say return the target of what I have over here with a reference of return the reference of the target, return the reference of the, so that works for constants, this works for regulars, mission accomplished. Now if I come over here, I'll see that I can actually print it. Or I want to say over here, see out, Q, that points to salary. I want to actually print the salary of the employee. How do I do the arrow? It's the exact same way. So I'm overloading the arrow operator, saying, hey, if the arrow operator is used, just return my address out. So type pointer, I'll return the address out and the mission accomplished. So it literally works like a regular pointer. Obviously, we can always set all the little good stuff for it. For example, if somebody wants to check to see what is the real address in memory, I can create a getter function for it. Or if somebody wants to check to see if the pointer is null, I can always have a Boolean operator set and check if it's not equal to null. So they can actually check and see and make sure that the pointer is in a good state or not, using a condition, exactly like they do with a regular pointer. And if they want to see what is the raw address, they will have access to that one too, so they can actually get the address out of it and take a look at it if they want to do anything with it. And also, if they want to compare this thing with null and see if the pointer is null or not, like a regular pointer, I overload the assignment operator and not equal operator for both of them. So they can actually compare my thing to null. If it is equal to null, I return that one, not equal, return that one. As easy as that. So if I am compared to a null pointer type, this is what I'm going to do. I'm going to compare it to null pointer. If I'm compared to null, not equal to null pointer type, I'm going to return that one. And that sets everything to. So there is absolutely no problem with that too. And we're done. So like this, my unique pointer works perfectly in all scenarios, and I don't need to use a regular pointer. Yes?
So, sir, did we just basically create a wrapper class for a pointer to
Yeah.
manage it better?
Yeah, exactly. It is exactly a wrapper class. It's a wrapper class around the pointer to manage it. So I don't have to worry about it. Because no matter what we do through that spaghetti code, we always forget to delete a thing or two. Like this, we won't. But one thing I have to tell you, with the unique pointer, we actually have a unique pointer in C++. So if you literally take this, okay, let me just do this. So let me just run this, see if it's okay, to make sure it runs. Okay, so this is good. This is running. Later on, walk through it. So I'm going to call this one GHI, unique UNPTR tester. Save. Okay. Now see what I'm going to do. I'm going to come over here, and instead of this, I'm going to put memory. Okay. And instead of this, I'm going to write unique PTR. And it works the exact same way. See? So the unique build errors, let me see why. Oh, Seneca namespace. Okay, so my apologies. My apologies. Yeah, so this works exactly the same way, no difference. See that? So, but please don't even imagine that I actually implemented it. The unique pointer that we have in C++ is much more sophisticated than this one, but this kind of gives you an idea of what they have done, okay? Because after I did the other sections, are getting a little surprised because the code changed over there because they found a few bugs over there, and I said I'm not claiming that I actually did that, but it's just very close to that, and that's what unique pointers are. Now, again, please be aware this is yeah. So in here I'm going to say J, and in here I'm going to call it the C++ unique pointer.
Can we see the source code of the unique pointer?
Pardon me?
Can we see the source code of the unique pointer?
You should be able to. You should be able to. I don't know if is allowed on Linux. I should have named it something else. Let me fix that first before we do anything. Can I rename here? Please allow me to rename. I should be able to rename. Save, close. No, I'll rename it. Yeah. I forgot how we did it, but when you are installing your C++, you can actually ask it to install the source code too. And then you can actually go through it. That's when I remember that long time ago I did that, so when you're actually pressing F11 on it, it will actually go to C++'s library starting to walk through the code that they have written. You can do that, but you have to install the source code with the compiler. Ask it. It's a special type of installation it needs. Google it or ChatGPT, it's going to tell you how to do it. But of course you can, yes. C++ is a very known language with all the compiler is pretty open. That's that one. And the next thing we said was a shared pointer. So the shared pointer is much more sophisticated because for a shared pointer, you cannot just delete the data. Imagine a shared pointer says, I want, if there are 3 pointers pointing to the same piece of memory location, I gotta keep track. So when the first one is gone and 2 is left, I shouldn't delete it. When another one is died, 1 is left, I shouldn't delete it. But if I'm deleting the last one, I should wipe the memory. That makes it a little crazy. I remember the first time I attempted, quickly I wrote a static variable to count the number of instances. But that doesn't work, because when you're actually, say you're using a shared pointer for a dynamic integer, if you are doing that, then you can have 3.3 integer shared pointers point to a dynamic integer and another 5 pointing to another. These all share the same static variable, so that's not going to work out. You have to have a counter for every new memory that is being allocated, and that makes it a little tough. Not too tough, but a little tough. I'll show you the code. So the very first thing that we need to do over here, again, let's actually create the thing, get a Okay, so the very first thing that we need to do is not only have a pointer that points to the actual data, but we need to create a dynamic counter that gets created when a new memory is being pointed to, and specifically for that one. So therefore, this pointer in each template can point to a different counter, and then I can manage to have a separate counter created, shared separate counter created for different arguments. To keep track of deleting all these, I cannot use a destructor anymore, a delete anymore. I need to write a delete that keeps track of how many things I have. So instead, I create a wipeout. Wipeout's job is to delete the memory of the two dynamic things that I have if this is the last instance. How does it work? First of all, somehow I'm going to create a dynamic integer counter for individuals. We'll come to that too. So imagine that we could successfully create a separate counter for individual dynamic memories that are allocated with a template. Then I need to be able to only delete if it's the last one. So what do? First, when the wipeout is counted, I'm going to first say, hey, does the counter exist? If it does, then reduce the target of the counter by 1. Now, reduce the counter by 1. If the outcome of that is 0, it means I was the last. One more time. If the counter exists, first reduce the counter by 1. If the outcome of that is 0, it means I was the last. You just delete me and I'm gone. Everything is deleted. Obviously, after that, I'm going to set it to null pointer. But if it exists and I reduced it by 1, it is not equal to 1. It means this object is dying, but the memory has to stay. Which means this object is being wiped out, but the memory is supposed to stay. Therefore, I just set my pointers to that location to null, but I don't delete anything. It means I'm not part of the family that is pointing to that pointer. I'm gone, but the rest will still have access. So that's wipeout. All I need to do whenever I want to delete, I'll call wipeout instead. Now, let's start. So the very first thing that I need to do is to construct from a raw pointer. So whenever the object is constructed, what I will do, I'm going to say, give me a new thing. As soon as you give it, because it's constructor, it means I'm the first. Constructor means I'm the first. If the constructor with a new is inside is called I'm the first, point to the pointer, and then if that pointer is not null, create a new size t and put the address over there. Otherwise, just put null in it. So if somebody calls this shared pointer with null PTR in here, I'm not going to add any counter, nothing. It means I'm null. I'm just an empty shared pointer. I'm not pointing to anything. But if I am receiving something to point to, I will create a size t and add it by 1, and that it means I am the first one who's pointing to it. Now, what if somebody wants to copy a shared pointer so two of them are supposed to point to something? Which means I want to share ownership. So what am I going to do? I'm going to say, okay, I'm copying somebody, fine. I'm going to point to its pointer, and I'm going to point to its counter, whatever it is. If the counter exists, it means that share pointer that I copied is not null. It's actually pointing to something. Add one to the pointer. Done. To the counter. Okay? So because it's prefix, I don't need to put parentheses around it, but I'm going to put it just to put emphasis. Okay? So I'm going to have one more owner. How about copy assignment? If one is set to another one, what does it mean? I'm a shared pointer. Either I'm not pointing to anything or I'm pointing to a piece of memory. If that's the case, I should be able to be assigned to another one, to go to point to another piece of memory. If that needs to happen, what do? First, I'm going to make sure it's not a self-assigned thing. Then I'm going to say, wipe me out, because I'm supposed to be set to someone else. Now, if I am pointing to a piece of memory and I'm not the last one, wipeout will simply set me to null. But if I am the last one, it will delete my resources. So everything is good. So wipeout is doing that. Now I'm going to say, I'm going to point to the other one, and I'm going to point the counter to the other one, and I'm going to add one to the counter. So I'm going to join the group. We good?
So, did I get it right? So every share pointer is like a node. Every node knows other nodes and the
No,
target.
it's not a node. It's like 10 people standing around each other, and they're all pointing to the same thing.
And they know each other?
No.
They count.
No, they just know how many they are. They don't know where the other person is. When I'm pointing, the only thing that they know that there are 5 of us that are pointing to this thing. But who the other people are, we don't know. Moving is easier. A move constructor steals ownership. No count change. I'm just stealing someone else's ownership. So I can simply say, okay, I'm just going to point to what you're pointing, and I'm going to make the other one null. I'm replacing another person. That's move constructor. Essentially, I am taking ownership. I'm stealing someone else's. But when it's move assignment, then I have to be careful. Why? Because I need to make sure that if I'm pointing to something, I'm not pointing on it anymore. First, I'm going to wipe myself out, get out of the group that is pointing. Then I'm going to join the other people. Replace ownership of the other one. And that's that. The rest, like one of the things that we have in here that we didn't have in a unique pointer, that we need to know how many of us is actually, how many owners we have for this piece of memory. And the rest is identical to a unique pointer. I'm not going to bother you with it because it's identical to that one with absolutely no difference. So the rest of the story is the same, which means I need to, the count is something that the other one doesn't have, but you should be able to get, you should be able to this, and all the things that you've done with the other one, you can do it over here too. And that becomes a shared pointer. Again, another wrapper around the pointer, but in a different way. So there are 2 possibilities, but You will see that we have many different, but we only teach you unique and share, but we have more unique pointers. We have more smart pointers, okay? If you like to see what are the other ones, please look at it. This is the extent of our kind of the range that we want to go. So this is this. And the shared pointer thingy, tester for this works like this. So as you see, I have P, that is new employee, P2, that is new employee, Q is nothing, R is there, I can say Q is equal to P, I can go R print, I can take the target, and when I'm gone, it's gonna delete everything properly. It really makes your life easier when you're actually doing dynamic memory allocation. Much easier. And just let's run it to make sure I don't have any boo-boos. So I have to redo them. There we go. All right. And as I mentioned for the other one, JK, share pointer tester. You can always remove that and go memory. And I don't need Seneca over here anymore. And you can say over here, shared PTR instead. And it works the same way. Oh, Control A, copy. Don't save. Yeah, so when I run this, it's going to work the same way. This is essentially the shared pointer, that C++ shared pointer. It works the exact same way. Okay, let me save this. First, I'm going to fix that. And that's that. Questions? Suggestions? Objections? We're good? That's smart pointers, okay? So please go through it and remember that what the quiz, what we're gonna have. I'm gonna put an announcement for it, obviously, but essentially, it's very simple stuff. So it's gonna be probably 15 minutes quiz, because you're essentially doing 3 seeks and a loop. That's it. I just want to see you do your seeks and stuff properly in a file. So you're using an F stream and you're opening for in and out, and you do the proper seek and you modify a few things and you're done. Okay, so I'll send you what the question is going to be. Please prepare for it and come. It's just a 20-minute quiz. I wanted to do algorithms, but I'm not doing it, so I'm splitting in 2 quizzes. The next week you're coming, you're going to do the algorithms. Okay? All right. Have yourself a beautiful day.